Okay. So, in the last class we started with analog signaler system, because our purpose is to go for digital filter design and digital IIR filter design, and digital IIR filters are designed by first designing an equivalent analog filter and then mapping it to a digital filter. That is why it is important to get back into this analog filter design concepts, and I just started giving you some background of original basic analog signals and systems. So, in the last class I discussed convolution, we discussed the delta functions, that is you start with one delta t, this delta t as this is say t minus t, and area is 1. So, 1 by 2 t, area is 1, and then let limit t goes to 0, this delta t, this becomes a function small delta which is called Dirac delta function. That is, if t becomes 0, but area is 1, gradually height will go up, further go up, in the end it will be and something like that, approaching function, okay, but it is continuous. So, that is why delta t dt was 1 and delta t was 0 for t not equal to 0, because delta t is, this small delta t is defined as capital delta subscript capital T small t with t going down to 0. Okay, that is why this has no value for t not equal to 0, value is 0. Then what I said is this, that suppose there is a function x t, x a t, and you want to see x a t delta t minus tau. Okay, t minus will be say t naught, t minus t naught dt. Okay, or instead of t, okay, it could be t, it could be tau, any variable. What will be this? So, for this you first start with this function here. Okay, this function, that is delta t, t minus t naught, this much is t naught, this is delta t, t minus t naught, and multiply x a t by this. So, this height will be modulated, by this part of the analog function, that will multiply the height. Okay. But slowly what will happen, but an area under this will be, you have to just carry out the integral area, like this will be the height. So, maybe it will be like this. Okay. So, under this curve whatever is the area, that will be this integral. But then to go to this small delta from capital delta, I have to make this height width is t, 2t rather, if we take this 2t, go to 0, and this will go up. So, when it becomes very narrow, this function, this is your delta t small t, and this is your center point is t naught, and this is your x a t. When you multiply this with this, basically this part will multiply this function, but this part, this is so narrow, the width is so narrow, there is hardly any variation here. So, you can approximate this function to be some constant at x a at center point t naught. So, now it will be a rectangular pulse only, height will be x a t naught times 1 by 2 t, earlier is 1 by 2 t, this is 2 t, and then slowly you make capital T go down further to 0, and this height will go up, but area under this will remain x a t 0, that is why this was x a t 0. So, that means x a t can be written as this way also, x a tau delta t minus tau d tau. Okay. Instead of integration variable small t, I am choosing small tau, and t minus small tau is same as tau minus small, delta t minus tau or delta tau minus t, they are same. Okay. So, small t now is acting like t 0 there, and tau is acting like t, and I have just reversed, because delta say t and equal to delta minus t. So, you can write this as delta tau minus small t, and small t is equivalent to t naught here, tau is equivalent to t here, and you get this. Then this we pass through a linear shift invariant system, linear time invariant system. Okay. This is the operator x a t, this is output y a t. You want to find out output y at a particular t of your choice. So, t working on this integral, integral is a summation. If system is linear, t over a summation of signals is same as t over the individual signals and their, so the response and the summation of the response. That is, first you if you combine the signals and then apply the operator, you will get the same thing if you first apply the operator individual components and then combine. That is the meaning of linearity. So, t will go into it, and this is constant because this is a function of time. Okay. This is a function of time. This tau is just a variable in the integration. Okay. You are just taking deltas over an infinite range from minus infinity to infinity, from on this axis from minus infinity to infinity as controlled by tau. So, for every tau there is a delta function multiplied by a constant x a tau, right. So, the operator t will work on the function of time, that is delta t minus tau, and then if system is time invariant, then if delta t has a response h a t, which is called impulse response, then delta t minus tau will have a response h a t minus tau, which gave rise to this thing, which was the analog convolution. Now, I will not go too much into all this. H a t minus tau d tau. In the previous class, I mean this we write as x a t convolved with h a t. In the previous class, we took t minus tau to be maybe tau prime. So, d tau was minus d tau prime. Okay, tau is t minus tau prime, and tau prime here minus comes out, integral limits get reversed because t minus tau is tau prime. So, when tau is minus infinity, tau prime is plus infinity, and when tau is plus infinity, tau prime is minus infinity. So, integral is from plus infinity to minus infinity, but outside there is a minus sign can be observed in the limits again, which means it will be from minus infinity to infinity, and that will become equal to convolution between h and x, and this is where I stopped, and I always tell you take this form for all practical purpose. Okay, here again the concept of causality and stability comes. Firstly, the integral can be written as two component minus infinity to 0 minus, that is approaching 0 from the left hand side, x a tau, and from 0 plus to infinity x a tau h a t minus tau d tau. Now, in this part tau is taking negative values, right, but anyway I will not rather take this form. As I told you, I will take this form. So, I was also making a mistake. Let me take that form. First h this will be up to 0 minus 0 plus this remains as it is. Now, look at this integral. Here tau is taking negative values from minus infinity to 0 minus, which means t minus tau. So, t plus some quantity, because tau is negative. So, minus minus plus, which means standing at time t, I am looking for future input, that is x a t plus something, because tau is negative in this integral. That makes it non-causal. In order to maintain causality, this should be 0 then over this interval. Here I have no problem, tau is positive. So, t minus tau means going, I mean t minus tau means I am going back in the past, which is fine, because past input is always known. But therefore, for causality h a tau or t or whatever be the way you describe, this must be 0 for t less than equal to 0 for causality. Similarly, for stability, I will take this second form only. I always told you the second form is always useful. Suppose input x a t for any t, it is basically its magnitude is less than equal to some m, that is there are two levels m and minus m, this is 0. So, input is always limited within this range, however large m is, and m is finite, that is x a t for any t is less than equal to m greater than equal to minus m, it is given. Now, mod of this is mod of this, mod of a summation, summation is integral. So, mod of a summation is less than equal to summation of mods. So, summation of mod of this product d tau is positive, mod of the overall product is mod h a tau mod into mod of this into mod of this, mod of a product is product of mods, we have already seen earlier. So, this will be h a tau mod of this, and this is positive. So, no point in taking mod there, and this is for any argument t or tau or t minus tau, this is less than equal to m. So, that means this integral is less than equal to m into d tau. Okay. Therefore, if it is positive, if it is finite, it is of course positive because mod is always positive, non-zero, non-negative, either 0 or positive, and integral be summed. So, this is non-negative, but if this is finite, the right hand side is finite. So, output magnitude is finite. So, output will remain within a finite limits. Then it will be guaranteed to be stable. So, that will be a sufficient condition, though it is not necessary condition. Even if this side is infinity, this is less than equal to. So, it could still be less than infinity and finite. But if this integral is guaranteed to be finite, then mod y a t is also finite. We have already seen in the discrete time case also. Therefore, for stability, sufficient condition that there is impulse response is absolutely, take absolute value, summable, that is integral is finite. It is very much similar to that. Next comes this eigen function, eigen signal approach. Suppose this is a linear time invariant system, so LTI, and it is characterized by impulse response HAT. Also, that if you take any function of the form a to the power t, where time t comes in the power, then it is an eigen function, because the output in this case is at any time t is a convolution, again the second form of convolution h a tau x a t minus tau d tau, but this is your x t. So, minus infinity to plus infinity, absolutely similar steps. X a t minus tau means a to the power t minus tau d tau, a to the power t can come out, integral is with relation to tau only. So, a to the power t comes out and integral is this. Sorry, this is a to the power minus tau. So, the entire thing after integration, there is no tau, it is just a function of a. So, you can call it an eigen value lambda a, depending on a, that a to the power t, output is lambda a into a to the power t. What is the advantage and all? We all know for this kind of functions, I mean you do not need to carry out convolution, you can straight away write down the output, just a to the power t only multiplied by an eigen value lambda a. A special case is when a is of the form e to the power j capital omega, omega, okay, capital omega. Omega is actually radian per second, because it will be the a to the power t means e to the power j omega t, radian per second into second equal to radian. The entire thing has to be angled, e to the power j theta, theta is radian. So, capital omega unit is radian per second of this form. In this case, this quantity, that is y a t is this quantity, and this quantity we write instead of lambda, we use the notation, it is a function of omega. A is nothing, A is basically a function of omega. So, it is basically function of, if you put this here, is a function of omega a to the power t. So, this where h is omega is this integral only h a tau e to the power minus tau means e to the power minus j omega tau d tau. This quantity is called analog Fourier transform of any signal h a t. Okay, you can have t here, tau here, anything here in the integral variable, no problem, any continuous variable. This is called Fourier transform. This is the genesis of Fourier transform. Now, it can be shown that you can get back this h a time domain function from this frequency domain function in this way by the inverse transform. H a t for a chosen t, so t is fixed, is 1 by 2 pi here integral is over omega. So, basically all frequencies are present for any capital omega, there is a carrier e to the power j omega t multiplied by an amplitude function, and this you are integrating, okay, and you get h a t. This is called inverse Fourier transform. This Fourier transform, this IFT, inverse Fourier transform, both analog Fourier transforms, right. Now, from this we can generalize, we can go to a more general transform which is called Laplace transform, and that we will do from here, in fact, from this one. Okay. Here you see e to the power minus j omega, but j omega is just purely imaginary, right. A more general complex number will have both real part and imaginary part. So, from j omega we will go for a more general complex number. Suppose I go sigma plus j omega. Okay. So, an integral of this form will be considered. I am not, that will not be this, make sure that will not be this, but this kind of form, this form I will preserve, but instead of just one minus and just one imaginary part only j capital omega, I will take a more general complex variable which will have both real and imaginary part. Okay, and I will assume that integral will be existing and all that, that is underneath. Okay. In that case, a general integral will be of this form. It is not, this is not this, I am repeating again, this is not this. I am trying to generalize this form here. So, I saw, okay, there is only one imaginary part, okay, j omega, just an imaginary part. Why not have a more general complex variable which will have both real and imaginary part. So, something of this kind. S, you can make it t also. Okay. So, this is more general integral and we will call it Laplace transform of HAS. So, HAS, and just to get back this Fourier transform, what you have to take, you have to make sigma equal to 0, that is real part of S. If you take 0, this integral will give rise to Fourier transform. So, this is more general than that, and I am assuming this integral will exist. Okay. This is called Laplace transform, but here S is a more general complex number. Now, for Hs to exist, this to be finite, that means this to be finite. Okay. But mod of this is less than equal to mod of e to the power minus sigma t e to the power minus j omega t, right. S is sigma plus j omega, so we break it like that, e to the power sigma t, and mod of the product is mod of this into dt. But mod of e to the power minus j omega t is 1. So, this is equal to and e to the power anything is positive. So, mod of that, no mod is required on that. Okay. So, you see, if this quantity, if this is finite, then this is finite and Laplace transform exists. So, this should be finite, but that has a beautiful meaning, that suppose I have got this complex S plane, this is a real part sigma, this is a j omega, and you have got suppose one line, vertical line. This vertical line means real part is fixed, and suppose I have S1 here, S2 here. S1 is sigma plus say j omega 1, S2 sigma plus j omega 2. But this condition, the H for this to exist, so for this, what is the condition? That for this to exist, the condition is absolute condition, sufficient condition is, you see, this should be finite, and there is no omega here. For this also, for this to exist, this should, that is, for this to be finite, okay, for any S1 is sigma plus j omega 1, it was for general S, now sigma plus j omega 1, S1 I am taking, this is the condition, this should be finite, but you see there is no omega 1 here, it is only sigma that matters. And for HA, that is why for HA S2, mod of that also to be finite, it said sigma is common, the same condition. So, this integral, if it is finite, then if I am moving on this line, any point I take, they all have the same sigma, only omega differs, this much is omega 1, this much is omega 2, but you see this existence condition, it has got no omega, because when you took mod of e to the power minus j omega t, it become 1. So, as long as sigma remains fixed, you move anywhere on this line, this integral will remain same, because there is no omega, it is only varying on sigma, and sigma is constant on this line. So, if you move on this line, if you take any s on this line, for any s, if you want to carry out the integral, you will only pick up the sigma from that s, not the omega. And so, therefore, if HAS1, suppose you are here and mod HAS1 is given to be infinity, that is, if this is for this, if this is to be finite, the same holds for HAS2 also, because for this also the sigma is same, which means here convergence is on lines, vertical lines, and not only vertical lines, if it is converging for one sigma, then from continuity, it is not that it will converge only at sigma to the immediate left of sigma to the immediate right of sigma, it will diverge, this will become infinity, this is not possible. Because of the continuity, there will be at least some strip, however small the strip, there will be some strip, however small the strip. Okay. So, this much is sigma, this much may be sigma 1, this much may be sigma 2. So, over a zone, not for a specific sigma, but because of sigma continuity, that is, if you put any sigma here, if it is finite, if you slightly increase sigma, still it will be finite because of the continuity, or if you slightly decrease sigma, still it will be finite. Okay. So, around sigma also there will be a small band over which this integral will be finite, and this always depends only on sigma, that is why I am not bothered about the vertical axis. So, that means this kind of region of convergence, that is the region in the space for which the Laplace transform magnitude will be finite, it will exist. Such region of convergence will be vertical strips. Okay. Now, if suppose the function is to be the signal, there is a sequence, there is a signal, not sequence, signal say x at, suppose there is an impulse response h at, I want it to be causal and stable. If it is causal and stable, firstly stability means, we know stability means, stability we have already seen, means that is stability, if you see this, if you take sigma equal to 0, then this integral, this condition, that summation minus infinity to infinity mod h a t dt less than infinity, that is also the stability condition. Therefore, if mod h s exists for sigma equal to 0, sigma equal to 0 means on this line, on this y axis, that is if h a s exists, that is its mod value is finite on this y axis means d omega axis for which sigma equal to 0. If you put sigma equal to 0, e to the power 0 1, so you get back summation integral minus infinity to infinity mod h a t dt less than infinity. That is the condition, but that is also equivalent to stability condition. isn't it? That is also equivalent to stability condition. So, we can correlate the two. We can say that if Laplace transform exists, that is the mod value of HAS is finite on the y axis, that is j omega axis, for which sigma equal to 0. That means that this sufficient condition is satisfied for sigma equal to 0, that is e to the power 0 is 1. So, what condition is satisfied? Integral minus infinity to infinity mod h a t dt less than infinity. Then, but that condition is same as stability condition. So, therefore, if the sufficient condition for the existence of Laplace transform on j omega axis exists, this is a sufficient condition. That is sufficient condition for mod of HAS, mod of HS to be finite for S on the j omega axis. If sufficient condition for that exists, is satisfied, that will be equivalent to stability. So, then the system will be stable, because on the j omega axis sigma is 0, e to the power 0 is 1, and whatever you get out of it, you get the stability condition. Therefore, for the systems to be stable, stability means ROC, region of convergence, must include j omega axis. That is, it may be a strip, around this, but it should contain the j omega axis. So, that this condition with this equal to 1 and this mod h a t integral minus infinity to infinity dt is less than infinity, that is satisfied, because on j omega axis sigma is 0. So, condition turns out to be that, which is again stability condition, right. On the other hand, if h a t is causal, then what happens? For that, you see one thing, suppose h a t starts from here. I will not give a full treatment. Suppose it is function like this. Okay. In this case, HAS is 0 to infinity, because integral function does not exist on this side. So, no point in carrying on the integration on that side. H a t e to the power minus s t dt, and therefore, mod HAS is less than equal to mod of a summation is less than equal to summation of mod h a t as before, and mod of e to the power minus s t you have seen, it is just e to the power minus sigma t dt. Suppose for some sigma equal to sigma 1, this is finite, RHS finite. Then for sigma greater than sigma 1 also my claim RHS will be finite, because as sigma, so for any particular t in this range, suppose you had e to the power minus sigma 1 t. Okay. So, this was multiplying by a damping function e to the power minus sigma 1 t. For the same t, you are now choosing mode value, I mean sigma higher than sigma 1. So, the value will go down, value of this, because of the negative sign, isn't it? E to the power minus sigma 1 t, if I now choose sigma 2, which is greater than sigma 1, I know sigma 2 t is less than e to the power minus sigma 1 t because of minus sign. So, earlier I was multiplying the function by e to the power minus sigma 1 t, but still this integral was finite, that is the assumption. Now, if I multiply by e to the power minus sigma 2 t, that means I am multiplying by lesser quantity and then integrating. So, obviously, it will be less than previous integral. So, obviously, previous integral was finite, this also will be finite. That means, in the ROC, in the S plane, if you have got some sigma 1, then all region to the right, for which if you draw vertical line, sigma value will be greater than sigma 1. So, all the region to the right of this line will be part of ROC, and then you start shrinking sigma 1, it can be going down to 0, or it can remain, I mean you go on shrinking it till the moment you reach a situation where if you shrink further, okay, the integral does not exist. So, you have to stop there. So, ROC will be I mean, you start from that line, go to the entire right, that will be your ROC. Okay. So, that means for causal systems, ROC starts from one vertical line, some vertical line, and then goes to the right. Now, if I want to have stability and causality, that stability requires ROC to contain vertical this j omega axis. Causality requires ROC to be to the right of some line. Therefore, both stability and causality means ROC is to start at a line to the left of j omega axis and go rightward. Since it is starting on a line and then going rightward, it is causal, and since it is starting on a line which is to the left of j omega axis, this region will contain the j omega axis and therefore it is stable. So, ROC in the left of plane, ROC should be like this. For a causal and stable system, it should start on a vertical line to the left of origin and go to the entire right. Okay. From this, we will arrive at the concept of pole and zero for these systems, rational systems here. Okay, and then we will talk of analog filters. Thank you very much.